Okay, here we are at looking at learning target number 3 now, and this has to do with analyzing a reaction for the purposes of balancing it, really. And a lot of times this is going to be our last step. Sometimes you might have to write a reaction, sometimes you got to predict the products, and then at the very end, we always want to balance in order to maintain conservation of mass. And today, you guys started watching the movie Einstein's Big Idea, and you can see where that came about. In Einstein's equation, E equals mc squared, we have m for mass, and that goes back to Lavoisier, who was this French nobleman. And like I said in the video, his main job was taxation. And so one of the things that he did was built a wall around Paris and taxed people every time they came in and out of Paris. And like they said in the video, that really did not endear himself to Parisians, because, as you might expect, if we did the same thing nowadays and built a wall around Olympia and had people pay a toll every time they came in and out of Olympia, that would start to upset people pretty quickly, probably. Um, so, the good thing about his job was that it allowed him, just really gave him the detail oriented, meticulousness that you needed to really carry out this kind of work to really say that mass is conserved. I'm not real familiar with the history, but I imagine that there were probably some scientists who may have suspected that mass is conserved. I don't know if that's true or not, but he was really the one to prove it. And then again, like they said, he had the resources to really build state of the art equipment at that time, to really go about doing the type of experiments needed to prove that sort of thing. Even though he was not liked among most of Parisians, he did contribute to science in the sense that he proved that mass is conserved. So again, if we look at a system, no matter how small or big that system is, and we look at all the mass inside that system, whatever that system started with, that system is going to end up with, even if you have all these different chemical changes taking place. And I think both in the movie and in the book, they kind of give the example of putting the city of Paris under a giant dome. And as as the French Revolution happened and all these things were happening, buildings were burning, things were being smashed. Of course, you would have some physical changes and some chemical changes happening in the city. But no matter what, whatever mass the city of Paris started with, that's what the mass is going to end up with after all the revolution took place. So, kind of a large scale system example there. A lot of you said you found this website and simulation helpful. I think if I am going to do this over next year, I probably would skip that first step with the tiles. I agree that kind of took a long time to pull all those tiles out. And even though some people found that helpful, I think a lot of people found it time consuming and even could be confusing depending on which tiles you pull out and what colors you pull out and so on. But the nice thing about the simulation is you get the same thing much more quickly, and it's actually pretty, in a lot of ways, whether you realize it or not, it's pretty real to life. So we talked about some of those trends, one of those trends being atomic radii, and you'll notice that the hydrogen atoms are smaller than the chlorine atoms, because again, it has to do with those trends. So there's a lot of things built into the simulation that are true to what we know about atoms. So this is one of those games again. I definitely come back to this simulation just to refresh before a quiz or a test. You guys know, when it comes to balancing equations, there are very various difficulties in these equations. Some are easy and quick, some are difficult and take a long time, even for people that have done them a long time like myself. So, by no means would I consider myself an expert. I would say I'm able to get most of these pretty quickly, but some of you actually got some quicker than I did, like those extra credit ones. Um, so anyway, just takes persistence. And like I was telling Kaylee, I think in sixth period, I kind of look at it like Sudoku. There really is, no way to do these. You kind of have to go back and forth. It's a little trial and error, but you will notice the more you do them, you start to develop strategies. And one other method I'll mention is that Kenny found out in sixth period. So this would be kind of for more of you students that are in Algebra 2, and that his method uses a system of equations, because we basically have, like for this example, we have three unknowns. We don't know what these three coefficients are in front of these different compounds, these different molecules. But you can probably get around it by a system of equations. And one thing we talked about was, which method's faster. And I think a lot of times trial and error are faster, but I think there are some examples where Kenny's method might be faster, the system of equations, so it just kind of depends. And anyway, just wanted to throw that out there as an alternative method for some people that are in advanced math right now. But so we're going to balance this again. Again, what we're doing is conserving mass. And really, again, keep in mind this is the beginning of stoichiometry. So when you get into chemistry, you'll notice this is important, because you'll have to make solutions possibly. And so you want to make sure that you're actually measuring out the correct amount of reactants and products and whatnot, to make sure you're actually doing the right thing chemistry wise. So anyway, this is one of the easier ones in the game. I would check out the introduction as well, because there's a couple tools in the introduction that are not in the game. So we'll take a look at that in a sec. But again, keep in mind, as you start to review here, you can say a lot more about this now. We didn't talk about this initially, but as you look at this reaction, you can look at it and know what type it is. It's a decomposition reaction. And also, again, we've got hydrogen and chlorine. Notice that hydrogen and chlorine, the two products, those two are by themselves. So that's why hydrogen is H2, and that's why chlorine is Cl2, because of Hofbrinkel again. So we've got two of each. We're going to need at least a 1 in front of all these. And again, you can see again, hey, I've got my hydrogen molecule, I've got my chlorine molecule. These are molecules because they're covalent compounds, or covalently bonded. And again, when you look at the trends, hey, these chlorine atoms are bigger than these hydrogen atoms. It goes back to that trend we talked about when we did the big periodic table. So a lot of stuff, you can see as we build on chemistry. So most of you are going to probably realize pretty quick, hey, I'm going to need 2 of these molecules in order for things to balance out. So, a lot of, again, this simulation made sense to a lot of you, I think, based on what you said in your reflections. And this is something that you guys can easily do. You can easily draw, and pretty quickly, I would think, these things yourself. So when you do this, if this is something that gives you trouble, take an extra minute or so to actually draw what you have there, because I think when a lot of you can actually see what's there, you'll probably end up balancing these a little easier. So I'm not going to go through the game again, because almost everybody did that, but let's just take a quick look at the introduction again. And we've got sound effects, looks like, as well. So you can choose different things here. Make ammonia. Again, this is going to be a synthesis reaction. Separate water. Decomposition reaction. And notice it says combust methane, because this is a combustion reaction. So I'm just kind of hitting some of those other targets as we go through this. But just wanted to give you, show you the tools. We got 2 different tools, this scale and these bar graphs. Maybe this helps some people, maybe not. So we're going to go through the same thing. We've now got these scales on top, which is basically telling us the nitrogen atoms on the reactant and product side, the hydrogen atoms on the reactant and the product side. And so just another way to visualize what's going on. So we've got 2 nitrogens, 2 hydrogens, again nitrogen, hydrogen by themselves. So Hofbrinkel, that's why it's N2 and H2. Over here we've got NH3. So just like before with the ion charges, if we have hydrogen, 3 of them, and 2 hydrogens over here, the least common multiple is going to be 6. So how am I going to get to 6 here? I need 3 times this. So I'm going to have 3 hydrogen molecules for a total of 6 hydrogen atoms. And notice on this side of the scale, I've got 6 hydrogen atoms. Of course, just like a teeter-totter, if somebody sat on one side and no one sat on the other side, it's going to be tipped in the favor of that person sitting on it. And over here, we need 2 nitrogens. So now that we've done 2 atoms of ammonia, 2 atoms of NH3, I've actually balanced the number of hydrogen atoms. But by doing that, I've also disturbed the balance of nitrogen. So I need 1 molecule of nitrogen. It's telling me now I'm good to go. I've got 2 nitrogen atoms on both sides, here and here. I'm seeing it here in the scale as well. I've got 6 hydrogen atoms, 2, 4, 6. 3 and 6 on that side. You see it here as well. 6 on this side, 6 on this side. Again, it's kind of telling us, hey, in as many ways we can visualize this, this is a correctly balanced equation. So good. Okay, and the other one is this bar graph. Again, just showing you a little differently. Now we're looking at this side, just like in the picture. This is the reactant side. This side is the product side. As I take away things, you can see things disappear, and of course, it's saying that these are not equal. So, it's just kind of showing us, and that's what I personally like about these simulations, is that you get that instant feedback, and a lot of times that's not possible in teaching. I used to coach before I taught, and in coaching it was a lot easier for me to give that instant feedback, and in some cases the athletes themselves get that feedback. But in teaching, it's hard to do sometimes to give somebody that instant feedback. But these simulations are really good for that. So I'm glad that a lot of you guys actually did see some benefit to doing this. And again, it is a good thing to revisit as we kind of look at this last test, and maybe even check out before the final as well. So that's gonna do it. Conserving mass. And hopefully you guys are enjoying that movie. That book is really good as well. That the movie is based on. I recommend you read it if you're interested in a little science. So, all right.